Hello everyone, I'm Paul and today we're solving problem 3027. Find the number of ways to place people to. This is a hard one, so next we will go with the visual step-by-step solution and then we will go with the code. If you haven't seen part 1 yet, I recommend you to go and watch that video. It's in my channel. The first challenge here is to understand this long description. I think this is overcomplicated. So just to be clear, we are given the coordinates for some points in a 2D plane. So let's say we're given this. Here is the visual representation of the points. And we need to find the number of pairs such that for each pair we have point A in the top left corner and point B in the bottom right corner. So this is a valid pair. Now, if we have some point in between these two, this is not a valid pair. So for this example, we have one valid pair here, another valid pair here, and another valid pair here. So we return 3. Now, if we consider these and these points, for example, this is not a valid pair because we have one point here in the middle. If we consider this and these points, for example, this is not a valid pair because this is not in the top left corner of the rectangle. So the first challenge here is to understand that this is basically the same as part 1. The only difference is here in the constraints. We can have up to 1000 points. This means we can't use a solution that runs in n cube. We need to think about something more efficient. We can think in terms of n square as a maximum. So now the question is, how can we go from n cube, which is the solution for part 1, to n square? So the strategy for this is the following. First, we want to sort the points. We want to be able to check for points from top to bottom and from left to right, meaning we care about this diagonal, okay? And after sorting, we get this. And now we can iterate each of these points in this order. First, we are here, next here, next here, next here. So we go first from top to bottom and then from left to right. We are starting here. And we'll have a variable, we'll call this minimum y. This is initially minus infinity. And first we are checking this pair. And let's see what's happening here. The maximum y, meaning the upper bound, is given by this limit. And the lower bound is given by this. It's currently minus infinity. Meaning if the next point is in this range, this means we found a valid square. Let's see what I mean here. First, we are checking this pair, and this is a valid rectangle. This is a valid pair. So we can add 1 to the result. This is initially 0, now it's 1. So now this lower bound regarding the y-axis is given by this, okay? By the y-coordinate for this point. Why? Well, because 1 is greater than minus infinity. So now the minimum y bound is 1. And we are still standing here. And what this means is right now the next point has to be in this range in order to be valid. So now we are checking this pair, meaning this square. And this is in this range, so this is also a valid square. We can add another 1 to the result, so this is now 2, and now the minimum y is 4. Why? Well, because 4 is greater than 1, so we replace this with 4. Now we are still standing here, and the valid range for the y-axis is this now. And we are comparing this point and this point. We are comparing this pair, meaning this square. Now, given that this is below the minimum y, this is not a valid square. So now we have tried every pair from this point. We have tried this and this, this and this, and this and this. Now we can move to this point. Now we are here. The minimum y is minus infinity again, meaning our current accepted bound is from here to minus infinity. And first we are comparing this and these points. We can forget about this now, meaning we can forget about this. We only care about this. So we are checking this square. Remember, this is the currently accepted bound, and this is above this. So this is not a valid square. Now we are still here and we are comparing this and these points, meaning this rectangle. And this is also not a valid square. This is not in the top left corner. So now we move here. We can forget about these 2 points, meaning we forget about this and this. The accepted bound from here goes from 4 to minus infinity. Okay, remember we always start with a minimum y of minus infinity. And we are checking this square, meaning this pair. So we know that this is greater than minus infinity and it's smaller than 4, and given that we are in the accepted range, this is a valid square. So we add 1 to the result. This is 3. The minimum y now is 2. Now we have tried every pair here, so we can just return 3. So basically from each point we are checking every possible pair. So when we are here, we check this pair and this pair. When we are here, we check this pair. And every time we want to keep track of the accepted bounds for the y-axis. When we are here, for example, the accepted bound goes from 6 to minus infinity. Then when we grab this, we move the lower bound here. Then when we are here, we move the lower bound here. And then when we are here, given that this is below the lower bound, this is not a valid square. Okay, so basically this is a very important variable. So now let's go with the code and hopefully you will get the idea. First, n is the length of points, and we want to sort the points by the y-axis in descending order and by the x-axis in ascending order. And there are basically 2 ways to do this. The first one is points.sort key equals lambda x, and here we take x1 reverse equals true. And after doing this, we can do the same for x0. And this is one way to do this. Now we have another way, which is to say here we have to put x0. We can forget about this. Here we add parentheses and x1 minus. So this and this is exactly the same. Now the result is initially 0, and for I in range n, for j in range from I plus 1 to n. And here we will say the maximum y is points I1, and the minimum y is always minus infinity initially. Okay, so now from here we can say points j, this has 2 values, we don't care about the first one, and y, and if the minimum y is smaller than y and y is smaller or equal to the maximum y. So if y is in between the minimum y and the maximum y, the minimum y is now y. We add 1 to the result, and finally we return a result. And remember that the borders also count. That's why here we use smaller or equal to maximum y. And here we use greater than because we start from minus infinity. If it's greater than minus infinity, we add 1 to the result and we update y. So now we have a point here in minimum y. So the next valid point has to be greater than this minimum y. So this is very important. Y has to be greater, strictly greater than minimum y and smaller or equal to maximum y. So this is it for the code. Now let's submit this and see if it works. As you can see, this works and it's very efficient. Now let me uncomment this and comment this just to show you this also works. And this also works. It's basically the same. Here time complexity will be big O of n squared overall, and space complexity big O of n because of sorting. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.